We use numbers every single day, but most of us never really think about their secret lives. It turns out the simple numbers we all learned as kids have this incredible hidden structure, a kind of secret code that powers our entire digital world. And today, we're going to crack that code together. So how do they do it? How can simple counting numbers create locks that are strong enough to protect global banking systems and top-secret military communications? That's the big question, right? And it's exactly what we're going to answer as we build our very own cryptographic toolkit right from the ground up.
All right, so here's our game plan. We'll start with the secret language of numbers. Then we'll discover their unique prime recipes. From there, we'll enter the really cool world of clockwork math, forge a kind of magic key to solve its puzzles, and finally, use our new toolkit to unlock the secrets of modern cryptography.
Okay, let's dive into section 1, the secret language. We're starting with the absolute fundamentals, the rules that are going to become the bedrock for all the powerful tools we're about to build.
All right, on to section 2. Unique prime recipes. This is the first essential piece of our toolkit, and it's all about those special numbers that are the building blocks of everything else. I'm talking about the primes.
So this leads us to this huge idea in math, the fundamental theorem of arithmetic. It basically means every number has its own unique recipe of prime ingredients. For example, the number 30 is always 2 times 3 times 5. That's it, full stop. No other combination of primes will ever give you 30. It's this absolute, rock-solid uniqueness that gives our number system its incredible power.
It's so easy to just take this for granted, but it's an incredibly special property. This one rule that every number has just one prime recipe is what gives our whole system its predictable, reliable structure. And as we're about to see, things can get pretty weird in other mathematical worlds that don't have this rule.
Okay, check this out. On the left, that's our world. Simple, right? 6 is just 2 times 3. Easy. But now look at the right. This is a totally different mathematical system where the number 6 can be made from 2 completely different sets of prime ingredients. Imagine trying to build a house if your bricks sometimes decided they were made of something else. Total chaos. That's why our rule of unique recipes is so important. It guarantees that our numbers behave in a way we can always trust.
Okay, section 3, clockwork math. It's time to add the next tool to our kit. So, we're going to say goodbye to that infinite number line for a bit and step into a world where numbers actually wrap around in a circle, just like the hours on a clock.
The idea is actually pretty simple. We just pick a number, we call it the modulus, and as soon as we hit it, we loop right back around to 0. Think about a 12-hour clock, right? That's what we call modulus 12. If someone says 15 o'clock, well, that's just 3 p.m. All we care about is the remainder after division. This finite circular world turns out to be the perfect playground for cryptography.
But, okay, there's a catch in this new universe. Addition, subtraction, multiplication, they all work just fine. But what about division? How do you divide 3 by 4 on a 12-hour clock? What does that even mean? It's not obvious at all. And solving this puzzle is the key to unlocking the real power of this entire system.
All right, section 4, forging the magic key. To solve this whole division problem, we have to literally forge a special tool, a key that's designed to work in this strange, new circular world.
And that tool is called the modular multiplicative inverse. I know it sounds complicated, but stick with me. In normal math, dividing by 5 is the exact same thing as multiplying by 1/5, right? Because their product is 1. We're looking for the exact same thing here, a special number that when you multiply it by your original number gets you back to 1 in our clockwork system. Finding this inverse is basically our version of division.
So, a fair question is, how do we even know the special inverse key exists for any old number we pick? Well, that's where this thing called Bézout's identity comes in. Think of it as the mathematical promise. It proves that as long as our number and our clock size don't share any common factors, a key is absolutely guaranteed to exist. It's the proof of concept.
But a promise isn't enough. We need a way to actually find the key, and we need to find it fast. And for that, we have the extended Euclidean algorithm. This isn't just theory. This is the high-speed, heavy-duty machine that actually forges the key. For the ginormous numbers used in real-world crypto, this algorithm is the only thing that makes finding that key even remotely possible.
And at its core, the algorithm is just a beautiful little machine. As you can see, you just start with 2 numbers and find the remainder of their division. If the remainder is 0, you're done. B is your answer. If not, you just swap the numbers and do it again. It's this simple loop that, by tracking its own steps,
can work backward to quickly forge the magic key we need, even for numbers that have hundreds of digits.
All right, section 5. This is it. This is the payoff. We've built our full toolkit. We've got unique prime recipes. We have our clockwork math, and we have our magic key forging algorithm. Now, it's time to put it all to work.
And that brings us to RSA. You've probably heard of it. It's maybe the most famous crypto system on the planet. And the coolest part? It's not some magic black box. As the slide says, it's literally just a combination of every single thing we've just talked about.
Okay, there is one last piece to the puzzle, and it's called Euler's theorem. This is the master rule for how exponents behave in our clockwork universe. In cryptography, locking and unlocking a message involves raising numbers to really big powers. This theorem is the rock-solid guarantee that the locking and unlocking process will reverse each other perfectly, every single time. So here it is, the complete RSA recipe, putting all our tools together. Step 1. The foundation. You pick two massive secret prime numbers, relying on the fundamental theorem for their uniqueness. This is where the security comes from. Multiplying them is super easy, but trying to factor them back apart is impossibly hard for computers. Step 2. The lock. You create the public key using the rules of our clockwork modular math. Step 3. The key. You forge the private key using our super-fast extended Euclidean algorithm. And finally, Step 4. The guarantee. Euler's theorem ensures that the key will perfectly unlock the lock. Every single tool we built has a critical job to do.
And listen, this isn't just some abstract math class problem. This exact mathematical process is happening right now, millions of times a second, all over the world. It's what puts the S in HTTPS when you're browsing online. It's protecting your emails, your bank account, your private messages. Your entire digital life is built on this very foundation of number theory.
So let's just quickly wrap up what we've learned. We saw that the unique prime recipe for every number is the absolute bedrock of our system. From there, we jumped into this weird clockwork math world using modular arithmetic. Inside that world, we forged the extended Euclidean algorithm as our super efficient key-making tool. And finally, we saw how all these kind of abstract ideas come together to create the very real engine of modern cryptography.
We've seen how the structure of numbers can be used to hide secrets in plain sight, creating the cryptography that basically runs our modern world. But the crazy thing is, the prime numbers themselves, those fundamental building blocks, are still packed with mysteries. Figuring out their pattern remains one of the deepest, most profound, unsolved puzzles in all of mathematics. So the real question is, what other secrets are they still waiting to tell us?